Dear fellow programmers, my name is Ingela Andin, and I work for the OTP team and have done so for many years. I do a lot of things, but my main focus, you might know, is TLS. And as for us humans, trust is so essential in so many ways. And when we are using open networks, such as the internet, trust is also of great importance. So we do everything on the net, from gambling, dating, organizing our lives, reading the newspaper, shopping, and banking. And for us to be able to trust these services is, or at least should be, very important. One of the most common ways to build trust in the internet is using TLS. That stands for Transport Layer Security. And it will try to provide three things for you. The first thing is data privacy. So only the sender and receiver of a message should be able to read it. And secondly, integrity. Nobody should be able to tamper with the message on its way through the network. And last but not least, authenticity. We should be able to verify that the sender and the receiver are actually who they claim to be. And this talk will focus on that part. And here is where the complicated part of trusting comes in. So previously, I have been giving talks about TLS the OTP way, where I explain why we implement transport layer security in Erlang, only using OpenSSL for the actual encryption, the number crunching. If you like to know more about this, you could read the paper that I and some co-workers wrote for the International Conference of Functional Programming this year. You can find it at this link. I could just mention that one of the reasons, of course, is that using a high-level language without explicit memory management and pointers makes us able to avoid some error sources that are hazardous, like, for instance, caused the very serious heartbleed bug in OpenSSL. So certificates are for a computer or for a network let me restart. So certificates are for clients and servers on the internet, as passports are for humans. Although for servers, the certificates are mandatory. But for clients, it's optional for the server to request it from the client. And of course, depending on what kind of server you have, the server might want to do that or not. Like the typical web server will not request a certificate from the client. Well, the trust that comes from certificates is mostly built on digital signatures. And so digital signatures can be accomplished by using many types of algorithms. But the concept is that you have some kind of data that the sender wants to sign. And in our case, it will be the certificate. And then you have some hash function, and you apply it to the data, and you get some kind of digest that you then can encrypt with your private key, creating a signature. And then you can send this signature along with your public key and the certificate to the receiver. And the receiver will now be able to decrypt the signature using the public key. And it, of course, has the data that we use to create the signature, so we can hash it. And we can verify that we get the same hash. And now we have verified the signature and know that it's the owner of the private key that actually created the signature. So what's the certificate authority? Well, it's someone that is trusted to supply certificates for clients and servers. And so if you are a client or a server, you will create the content of your certificate, and you will take your public key and you will send it to the certificate authority, and they will say, okay, we can authorize this, and they will sign it with their private key and send you back the valid certificate. And you can have lots of certificate authorities and certificate authorities that verify other certificate authorities. And in such a way, you can build a chain of trust. But at the end, you will have a root certificate that is self-signed. And of course, you need some kind of other mechanism to trust this root certificate that is not a digital signature. And you can compare this to like how passports works for people. So if you need to get a passport in Sweden, you would go to the Swedish police, and they will issue you a passport. When you renew it, that you take your old passport so that they say, okay, you are you, and they will give you a new one. But the first time, they need to build this trust in some other way. And it's usually you have two other persons that already has a passport that will vouch for you. So normally it would be your parents, but it could be like two other people. And so in the end, the police has to build their trust in some other way than their own knowledge. And it's the same for certificates. You have to have some other way to trust them in the end. So a certificate chain, it could look something like this. So you have, can you point with this? How do you do that? Well, okay, at the top you have the end entity certificate. That's the certificate of the client or the server. And it will have a reference to its issuer. That will have a reference to its issuer, and so on until you reach the root. And the certificates will be signed by each other. And well, in the best of worlds, this will be the case. But if you have a really old version of the certificates, the name reference might be missing. And then creating the chain is a really brute force task. Actually, I hope such certificates doesn't exist anymore. But we still have code to handle that case if it should appear. So what a certificate looks like is defined by a so-called public key infrastructure. And it's specified by ASN.1 specifications. And we have built a public key library application to handle these certificates and their formats, and also the verification of the certificates. So a typical certificate, it has a version number, a serial number, signature algorithm. It has the name of its issuer, hopefully, and the validation period, its own name and its public key, and there can be some extensions that are optional. And you have the signature algorithm and the actual signature. So, when validating the certificate chain, it's also called the path validation. It has a specified algorithm in RFC that you can implement. And it's actually going through the certificate chain backwards. So you start at root, And the root certificate is more of an input to the validation. It's really not part of the validation. The only thing that you actually check is that it has a valid date, because it's self-signed, so of course it's going to be, the signatory is going to check. And then we have to recurse through the certificates in the chain and do all the checks that you should do. And you need to check the extensions and the issuer and name constraints, and you need to verify the signature, and there could be application-specific checks that you can, so we have a callback via our verify fund so that you can check them too. And of course, I or anybody else at the OTP team, we cannot tell you who to trust. So the certificates to trust needs to be an input from the application. And I mean, most web servers, they will trust the certificates that come with the operating system. And we have a public key function to help you load this if you are building a web service or a web client of some sort. But of course, this is not the certificates that your bank is going to want to trust, or any company building some other service. They don't want to trust these certificates. And additionally, to all these checks that are in the RFCs and that you should do, if you're a TLS client, there's an additional check that is actually not part of the TLS standard, and it's not part of the path validation algorithm, but it's deemed essential, and it's easiest to do in the context of the path validation. And it's checking that the host name that will be provided by the client is equal to what the server name has put in its certificate, saying this is the server that I am. So it should be really easy, like piece of cake, right? Well, there is some snags. It's actually not until TLS 1.3, that's the latest version of the protocol that came out in 2018, that this extension is actually mandatory. So what do we do then if it's not present? Okay, people are saying you must do this check. Okay, so we are doing our best. We will use the host name that was used to create the TLS socket. But it could be an IP address, and yeah, that's probably not what you want, but it's the best we can do. And actually, the server name in the certificate, it's not mandatory either. So we fall back on the common name, and yeah, that is what certificate will do, all TLS implementations will do, so yeah. But to make it even more complicated, some of the protocols running on top of TLS will say that we could allow wildcards for this check. And they don't agree on how to do these wildcards. They have different rules. So we can't have a solution that works for everyone. So we have a callback for this. And to help people, we also implemented HTTPS and LDAP version of the rules in the public key. But the real headaches comes from people breaking the specifications. So ACE and Net.1 compilers don't seem to be that common out there. So many people kind of roll their own. And they don't check all the constraints that the specification supplies. And then some encoders, they're very sloppy, and they don't check either. So a lot of TLS implementations will validate invalid certificates. And then they will send us error reports because we have a real ASP.1 compiler that checks the constraints. And they say, okay, this implementation over here, it accepts this certificate, so it's a bug in your implementation. So actually, we have a pull request that wants to allow the verify fun to accept and validate some date formats that are not valid. Because they say, well, our hardware is creating these certificates, and this is a big problem for us, and you're just the software, so you can fix it for us. And then we have country names, or country code names, country codes actually. And they're supposed to be 2 letters, and they're supposed to be US ASCII. But there are also other country code systems in other places where you use 3 letters. And a very common mistake seems to be using USA instead of US. So, okay, well, that might be an honest mistake. So, okay, we have a workaround for that. But we're not allowing long country names of any length. That's just insane. So we're not doing that. But also, it's quite common that they will encode it as UTF-8 instead of US ASCII, which is not really a problem because the letters will still be the same conceptually. So we have a workaround for that too. But the worst deal breaker actually is sort of a configuration error. So, you know, there's the certificate chains, and many systems, you configure them through PEM files. And the PEM file, it looks like this. Okay, so you have a begin certificate and you have an end certificate. And in the middle, you have this dir blob that is base64 encoded. And it makes not so much sense to humans. Okay, so the certificate chain, it has to be in the correct order for the verifying algorithm to work. The verifying algorithm assumes that you are feeding it in the correct order. So you can imagine then when you use this kind of file to specify the chain, and you leave it up to the humans to make it in the correct order. You can imagine what happens. So let's take a look at certificate chains. So according to TLS 1.2 specification, a certificate chain has to be a complete certificate chain, starting with the peer certificate and including all the certificates until the root. And all of this needs to be sent to the other side, except for the root certificate, actually, because you need to own the root certificate and you need to obtain it in another way than the sender sending it to you, because otherwise you don't know that you can trust it. Okay? And also the public key infrastructure says that, okay, you can actually put your trust in an intermediate certificate, which means that you shorten your chain. And then you will take like the intermediate certificate 1 and use it as the root certificate when you do the path validation. But due to these configuration errors, we also get incomplete chains where there are certificates missing. And then we can't verify the chain unless we happen to own the certificates that are missing from the chain, because then we could recreate the chain and actually verify it. And also a common case would be that you get a chain where you still get the peer certificate first, because they usually get that right, because usually you have a peer certificate in one file and the chain in another file. So you might get the chain in some kind of arbitrary order. And then you could try to sort it and then verify it. And lots of TLS implementations actually do that. And we were very reluctant to do this because even though we couldn't see like any big problem except for it making our code complex and slower, we don't like to break specifications. But then TLS 1.3 came along and said, okay, you should actually try to handle this. And you should do it also for 1.2. So, okay, they specified we have to, okay, so fine, we'll do it. And so we support this from OTP 21. But as a sidetrack, I would like to tell you a little more why we don't like breaking specifications. And it's about the poodle attack, actually. I don't know if you heard of it, but it was discovered by Google in 2014. And it's an ingenious attack where you manipulate some block cipher padding, and then you observe the different error messages that you get from the TLS stacks, and gradually being able to decrypt the message. And the funny thing about this is that TLS 1.0 specification says that you should do this padding check, but it's not mandatory. It's like you should, but you don't have to. Actually, we had a problem interoperating with Google servers when we did the check. So we thought, well, the previous version of TLS doesn't specify this check at all, and it's just checking that the padding are only zeros. So it seems not so harmful. We will remove it because not interoperating with Google is kind of suicidal. So we took it away. And then Google found this attack. And of course, they fixed their servers, and we could put the check back. But back to certificates. Another problem with certificates is that when they expire, your typical web client would look like this before they have a chance to update all the web clients. So then somebody thought, well, we need a more soft upgrade of certificates. So they thought we could send some extra certificates in the chain so that depending on which root certificate you actually own, you could create two different chains. And so then you could have like a time slot where you could have both the old certificate and the new certificate working for the client. So you can have a smoother upgrade. So this could look something like that. And this kind of explodes the number of chains that you could actually build. But yeah, we handle this too. We have some constraints so that you shouldn't be able to DOS attack our service. But this also created some other interesting problems because of handling all of these different types of chains. We needed to have logic in our SSL application that actually decrypt or decoded the certificates earlier. Because before, public key would do the decoding. And the public key algorithm still wants the certificates in the correct order to work. So we have to do all this pre-processing in the SSL application, and then we had to decode the certificate, and now the decoding work will be doubled. So it will be done both in SSL and public key, which is a bad thing. So our first approach was to just feed the decoded certificate to public key instead. It actually handled that, so it should work, right? Well, actually, the path validation also verifies the signature, and then you need the original encoding to be able to verify the signature. And so, of course, public key is capable of encoding it again, but due to all our workarounds, encoding wouldn't always be giving the exact same result as the one that you received on the wire and the one used for the signature. So actually we had to make our public key application take both the decoded and the encoded version of the certificate. And additionally, if something goes wrong with the key, if your key is leaked, I mean, you should keep your private key really private, but if it's leaked, or also for other reasons, like if the company or the person owning the certificate goes bankrupt or something, you might want to revoke the certificate, and you need to check this to protect the users. And the initial way of doing this, specified by the public key infrastructure, was something called certificate revocation lists. And they have like a global dedicated server for having this file that will grow and grow, becoming a much bigger file, and you will want to cache it. And also these servers are normal HTTP servers and LDAP servers, and so they can be vulnerable to other sorts of attacks. And you kind of will get the best effort because you don't want this check to take too long time. Of course, we have in public key, we have all the code to verify your CRLs. But building the cache is sort of still the application's job. And we have some callbacks in the things to make it a little easier, but it's still the application that needs to do that. And later, of course, the standard invented so-called CRL distribution points, so that you were able to have load balancers, for instance, to make this process a little less expensive. But it's still not perfect. And there's also another approach called the OCSP protocol. To the best of my knowledge, mostly used by clients. And it lets you query this OCSP service about the specific certificate. But still, if you are connecting to many different kinds of servers, there will be many requests. And this service can also be vulnerable to man-in-the-middle attacks if its key is exposed. So it has its own problems. And finally, there's a way of like turning the tables and making the server contact the OCSP service and then staple the result into the TLS handshake, which is considered better. And this is something that we're actually working on supplying for our clients. So, as in real life, trust is hard and complicated. But it's really essential, and there's like no better alternative. So we will continue our quest to help provide you with the tools to build trust for your applications in Erlang OTP or Elixir Ditto. Thank you for listening.
Thanks very much. Anybody have any questions?
So let's say I'm playing with client node in Elixir and server in Erlang and trying to connect to them each other with TLS through our standard applications, and I'm getting strange errors. And because this is like OpenSSL, so C code, do you have any tips to debug this kind of problems? Because it's really confusing sometimes. Like sometimes you can read just, okay, this is CI problem, your certificate is not validated, and Erlang just provides the same error that OpenSL provided, but sometimes it's like manufactured message and...
Well, I mean, there are several ways. It depends on what your problem is, and we're also working on including more error messages in our logging, or more information when we log things. But the TLS has like a standard alert protocol that says if this happens, you should send this kind of alert, and that is what you will get on the other side. But on the side creating it, you will get hopefully more information from the logs. We also have a debug logging mode for TLS, so you could turn it on, and you will get the log messages telling you what the TLS messages looks like, and you can see which algorithms were included and in the hello messages and so on.
Thank you.
Another question? Yes.
First, I want to thank you for maintaining this, because SSL has got to be one of the most complex realms that we have to deal with.
Yeah, it is kind of complex.
Yeah, anytime I have to touch SSL, I'm like, okay, here's 2 hours. But I also wanted to thank you for adding get certs and using system locations, because that does make things a lot more simple.
Yeah, and it makes a lot of sense for web applications, but our TLS application is a more low-level API, so that's why they said, yeah, this is good for web servers, but not everyone wants to trust these certificates, so we can't have them as a default to SSL, but of course we have them as a default for our HTTP client now.
Yeah. Also great. Thank
Yeah.
you. Thank you very much.
Anyone else? All right. Thanks again.